Hello, and welcome to today's third seminar in the series of Cornell Princeton Network Programming seminars. My name is Mohammed Shabazz, and today I'm going to talk about our work on PISCES, a programmable protocol-independent software switch. It's a joint work with folks at Princeton, Stanford, VMware, and Barefoot. Before we start, I would like to mention that we will have a Q&A session at the end of this talk. So if you have any questions during the talk, please post them in the live chat window to the right of this video, and I will answer them at the end. SaaS networks today, such as networks in large data centers, contain Ethernet switches that are built using fixed function switching ASICs. These switches usually support a large but fixed set of protocols that are hardwired into an ASIC when it is designed and manufactured. Therefore, we cannot typically add or remove the protocols after the ASIC has been built. However, lots of work is going about building fast programmable switching ASICs. There are many reasons why people want programmable ASICs. First, so that they can quickly and easily add new protocols. For example, it took industry 4 years to add VXLAN to Ethernet switches, which is now the most profitable and fast-moving sector in the networking industry. If we instead had programmable switches back then, we would have been able to add new features in hours rather than years. Second, so that we can quickly and easily remove unnecessary protocols. Simple networks are more reliable because there are less things that can go wrong. So if we can remove protocols we do not need, the network is less likely to fail under misconfigurations and is easier to debug when it does. Also, removing unused protocols free resources for other protocols to use. Thus, such customizations are already being made in various networks for these reasons. For example, data centers that host Amazon Web Services are known to forward packets using only layer 3 headers. Having programmable switches would make these customizations faster and easier to implement. The third reason is to gain better visibility in the network. There is huge interest right now in seeing what the networks are doing. For example, we have seen papers on packet level telemetry, and products like Cisco Attrition promise greater visibility into what the networks are doing. Having greater visibility makes it easier to identify applications that are faulty, causing congestion, corrupting forwarding tables, and so on. The key idea here is that when a network fails, a team must be able to quickly identify the bug and fix it. Programmable switches make this possible using methods like in-band network telemetry. And finally, the final reason is to perform network functions at the switch itself. There is active work going on in finding methods to perform certain network functions that are currently part of middle boxes with programmable switches. For example, there are efforts in exploring the possibilities of doing load balancing, for example, Hula, or to implement even more complex protocols such as PISCES using programmable switches. So the main idea of a programmable switch is that it is a generic engine that does not know how to process packets beforehand. We can then program it to support all existing protocols, or can easily remove unnecessary protocols, or can even add our own new custom protocols. In recent years, we have seen efforts such as Intel's FlexPipe and programmable switching chips from startups like Xpliant and Barefoot. We can see that all this work is going to help us program hardware switches. However, there is a missing picture here. Consider the modern-day virtualized data center. In these virtualized data centers, each server is running multiple virtual machines running on the server managed by a hypervisor. And in each hypervisor, there is a software switch that passes data between the VMs and from the VMs to the outside world. We can see that these software switches are serving exactly the same function as hardware switches, which is that they route packets between different networking entities. Also, one interesting point to note here is that there are now more virtual ports than physical ports in these modern-day virtualized data centers. In fact, since 2012, there have been more Ethernet ports in the software than in hardware. So we can easily see the importance of these software switches in the modern-day virtualized data centers. Okay, so it seems like it's easy to assume that since these software switches are defined in software, they should be easy to program and modify. Well, what we found out is that that is not really the case. And let me tell you why. A software switch is based on a large and complex um, body of code base, like kernel, DPDK, and more, that is needed to set up the machinery for fast packet I/O. And at the same time, one has to specify the logic for packet processing, like parser and match action pipeline, using arcane methods like exposed by these complex code bases. Thus, making changes in these software switches is a formidable undertaking, requiring uh, domain expertise in network protocol design and software development to build, test, and deploy these large code bases. Also, it can take 3 to 6 months to push a new feature into the mainstream code. For example, a usual kernel release cycle is roughly 2 months, and then it can take years to push the changes into the Linux distribution, like Ubuntu and Fedora. Furthermore, customizations require not only incorporating changes into the switch code, but also maintaining these customizations across different versions of the switch. However, there is a conflict here. As protocol designers, we are interested in specifying how to parse packet headers and the structure of the match action pipeline. That is, what headers fields to match on and what actions to perform on the matching headers. We do not need to understand the complexities of the underlying code base and the arcane APIs that they expose to enable fast packet I/O. So what should we do about this? How should we address this conflict? How about we separate the packet processing logic from the switch and specify it using a high-level domain-specific language, and then compile it down to the underlying switch, letting the compilation process taking care of the arcane APIs and complexities provided by these various large and complex code bases. A natural question then to ask is, what domain-specific language should we use for specifying the packet processing logic? For this work, we chose P4, a high-level language for programming protocol-independent packet processors. It's an open-source language that lets the programmer describe different aspects of a packet processor, like packet headers, metadata, parser, actions, match action tables, and control flow. Now, using P4, a protocol designer can specify the packet processing language of the native OVS using roughly 300 lines of code, whereas it can take roughly 40 times more lines of code than writing the same logic using the APIs exposed by the underlying code bases. So again, we see for a protocol designer, separating the packet processing language logic from the switch clearly has its benefits. And we will quantify such benefits in more detail in later part of this presentation. Also, as we are combining a P4 program to low-level APIs provided by the kernel or DPDK in OVS, therefore, this compilation process can incur some overhead on performance. We measure this overhead by comparing the performance of the native OVS, a handwritten software switch, to a modified version of OVS that is programmed via P4. In this work, our first goal is to quantify the reduction of complexity, that is, the ease with which a programmer can express new protocols in P4 versus directly modifying the OVS source code. Second is to implement performance optimizations to reduce the additional overhead on performance when compiling a P4 program to OVS. To study these goals, we implement PISCES, a software switch that allows custom protocol specification using P4 without requiring direct modifications to the OVS source code. A P4 to OVS compiler in PISCES compiles the P4 code to OVS. It generates the necessary parse, match, and action code needed to build the corresponding executable. Okay, let us now look at our first goal, that is to quantify the complexity of developing and maintaining custom protocols in P4 versus direct modification in the source code, in the OVS source code. We evaluate two categories of complexity. The first one is the development complexity. That is the amount of effort needed in building baseline packet processing logic for a software switch, or in other words, building a switch from scratch. The second one is the change complexity, which is the effort needed in making and maintaining a change in an existing switch. So as I have mentioned earlier, building a switch requires specifying both the packet processing logic along with the underlying machinery for fast packet I/O. For example, in DPDK, this means specifying the header files and libraries containing DPDK-specific methods and interfaces. then initializing the code for the DPDK environment and allocating memory, specifying the code for initializing the cores, the queues, and then the ports that will receive the packet. And then to write a packet processing loop that will receive the packets on these ports and then process them. Finally, after all this is done, the programmer then specifies the packet processing logic. Again, as a protocol designer, again, we can see that this is point number 4 is what we are interested in, which is the packet processing logic that we would like to specify to tell the switch what we want it to do. And we are not actually interested in all the other low-level details about the underlying technology, like header files, environment, memory, cores, and queues, and so forth. Also, in OVS, the match action pipeline is written using a slow path, and then there's a cache in the fast path for fast packet processing of the packets. So now, as a protocol designer, we not only have to specify the logic for the match action pipeline in the slow path, but we also have to specify the code for the fast path as well. And along with that, we also have to specify the command line utilities for adding or removing flows and querying flow and other statistics from the switch. And along with that, we also have to specify the interface between the control plane and the switches, for example, OpenFlow. So instead of taking this bottom-up approach, in P4, we take a more top-down approach. We only write code we need to specify how a packet should be processed. For example, packet and metadata headers, parser, match action tables, and control flow. And then finally, PISCES compiles this P4 program to OVS. So let us first look at the development complexity. We compare the native OVS with the equivalent baseline functionality implemented in PISCES. We use 3 metrics: lines of code, method count, and average method size. Again, note that these measurements only consider the set of code that is responsible for match, parse, and action. We see that PISCES reduces the lines of code by about a factor of 40 and the average method size by a factor of 20. So again, we can clearly see that this decreases the amount of effort for a programmer in order to specify the logic or the program that it wants to specify for the switch to perform. Second, we evaluate the change complexity. We compare the effort required in adding support for a new header field in a protocol that is otherwise already supported in both OVS and in PISCES. We add support for 3 fields: connection label, tunnel OM flag, and TCP flag, and measure how many lines and files are changed in adding these fields. We see that modifying just a few lines of code in a single P4 file in PISCES is sufficient to support a new field, whereas in OVS, the corresponding change often requires hundreds of lines of changes over tons of files. Okay, so does this mean that PISCES reduces complexity? Well, yes, it does. The resulting code simplicity should make it easier for protocol designers to implement, deploy, and maintain custom software switches. Okay, let's move on to our second goal, that is the performance optimizations. I will first talk about the forwarding model for both P4 and OVS, and then I will show how a naive mapping from P4 to OVS can lead to performance overhead. And finally, I will discuss different optimizations that we have implemented to reduce this performance overhead. In P4 packet forwarding model, a packet parser identifies the headers and extracts them as packet header fields that are essentially a copy of the content of the packet itself. The checksum verify block then verifies the checksum based on the header field specified in the P4 program. The match action tables operate on these header fields. A custom checksum update block updates the checksum. Finally, packet deparser writes these changes back onto the packet. Again, in this design, because the changes are being applied at the very end of the pipeline, we call this editing mode a post-pipeline editing mode. On the other hand, in the case of OVS forwarding model, the packet parser first identifies the header fields. However, it doesn't maintain any copy of those header fields. It then forwards that packet to the match action cache, and because the cache is seeing the packet for the first time, it will see a miss, and that packet is then punted into the match action table. The match action table will then process the packet and install a new flow rule in the cache, and then will forward that packet out through the egress. Next time, when the same packet comes for the same belonging to a same flow, the packet parser again identifies the header field, sends it to the match action cache, and then because this time there is already a flow rule in the cache, the packet will be processed by the match action cache itself and will be forwarded out to the egress. So again, in the OVS forwarding model, we see that we are not maintaining any extra copies, and the changes are being applied directly onto the packet itself. So we call this mode of editing an inline editing mode. So in order to map P4 to OVS, we modified OVS to support both of these editing modes. And we call this modified OVS model a PISCES forwarding model. So now the problem is how to efficiently compile the P4 forwarding model to this modified OVS forwarding model. We see that in a naive compilation of our benchmark application, which is essentially a router with an access control list, shows that PISCES has a performance overhead of about 40% compared to the native OVS. We observe that there are two main aspects that significantly affect the performance of PISCES. The first one is the number of cycles consumed in processing a single packet. And the second one is the number of cache misses. To understand the causes of CPU cycle per packet, we looked at the cycles consumed by each component of the forwarding model in the fast path. We see that the packet parser is taking roughly about 76.5 cycles on average, compared to the native OVS, which is only taking roughly 43.6 cycles on average. In the case of the match part of the cache, the performance is comparable in terms of the CPU cycle. And however, in the case of the action part of the cache, we see that there is a roughly 2 times increase in the CPU cycle per packet being consumed by PISCES versus the OVS. And finally, because of the added amount of CPU cycles being consumed in PISCES, we see that the throughput is much less than the throughput of the native OVS in the case of PISCES. So we studied different factors that affected the CPU cycles per packet. And I will now talk about 3 of them here. The first one was the extra copy of headers that are being maintained in the default PISCES forwarding model. And then the second one is the fully specified checksum that we specify in P4, and then parsing of unused header fields. P4 by default assumes a post-pipeline editing model. Thus, it requires keeping an extra copy of headers, as shown earlier. The post-pipeline editing mode requires maintaining an extra copy of headers, whereas inline editing mode doesn't require any extra copy. We found that maintaining these extra copies has a significant overhead. For example, while using a tunneling protocol like VXLAN, the post-pipeline editing mode consumes 2 times more cycles than inline editing mode. But on the other hand, in case of post-pipeline editing, packet is adjusted only once. That is, the changes are applied only once at the end of the match action pipeline. Whereas in case of inline editing, packet is adjusted and changes are applied on every action. Adjusting packets has a very high toll on performance, as can be seen in this graph. Based on our micro benchmarks, we observe that if the number of adjustments are less than 6, we should use inline editing mode. Otherwise, we should use post-pipeline editing mode. Thus, we came up with the following optimization. We call inline versus post-pipeline editing. At compile time, we analyze the P4 program to find out if the number of adjustments, for example, the add and remove header actions, are less than the specified threshold. If they are, we use the inline editing mode. Otherwise, we use post-pipeline editing mode. So in our benchmark application, the number of adjustments were less than the threshold. That is, it only does VLAN encapsulation and decapsulation. Thus, the compiler, based on that analysis, uses the inline editing mode for this program. Based on that, the compiler generates a code where parser doesn't make a copy of headers, and thus no packet deparser, but deparser stage is required in this case. So after the compilation, this is how the final pipeline looks like for our benchmark application. So again, looking in terms of the CPU cycles, now based on this optimization, we see that the benchmark application, so in our benchmark application, now the parser is taking roughly 2 times less cycles than the naive compilation, and because of that, we see roughly 300 megabits per second improvement in the overall throughput. The second factor is the fully specified checksum. So in the P4 program, by default, the programmer specifies the checksum in its entirety. That is, for example, if you want to do IP checksum, you will specify all the 12 header fields that you want to use to generate that checksum and then verify the checksum. Similarly, in the case of checksum update, you will again specify all the 12 header fields in the IP header to generate the checksum and then update the checksum on the packet. So this also provided us with an opportunity to implement another optimization. In this case, what we did was we provided the programmers to inform the compiler whether the switch is a part of an end host stack, or whether it is running as a transit switch, or if it's neither of the two modes. So in the case of when the switch is a part of an end host stack, what we do is because the switch is now running as an end host, running on the end host, so we no longer require the update part because the end host will consume the packet itself, and there is no need to recompute the checksum and then update it at the end host itself. So this is how the final pipeline looks like after the optimization. And if in the other case the switch is running as a transit switch, then in that case, what we can do is we can actually remove the checksum verify part and replace the checksum update part with an incremental checksum update logic. And also, what we do is like we analyze the match action pipeline in the P4 program and then find out which of the fields that were initially specified in the checksum update function out of which have been modified. And then based on that analysis, we see, okay, which of these fields have been modified, and then we only run the checksum update for those header fields. And so this is how the final pipeline looks like. So again, in the third case, if we see that the switch is neither running in the end host stack or is neither running as a transit switch, then in that case, we will have to keep the checksum verify stage to verify the checksum, but we can still replace the checksum update part with the incremental checksum update logic. So again, coming up to our CPU cycles table, now we see is that in the case of cache actions, but changing from the default checksum update logic to the incremental checksum update logic, we see that there is roughly 2 times decrease in the number of cycles being consumed compared to the naive compilation. And the throughput is now significantly increased up to 12.6 gigabits per second. Our third sector was parsing unused header fields. So what was happening in this case was the parser was actually parsing all the 3 headers, the layer 2, layer 3, and layer 4. However, in the case of match action pipeline, for example, we are only operating with the layer 2 headers. Then in that case, using program analysis, we can actually remove the remaining 2 headers as dead code and can further optimize the parser. So after running that optimization on our benchmark application, the number of cycles that were being consumed by the parser were actually dropped down by roughly 10 cycles. And then we saw an increase of about 200 megabits per second in throughput. So okay, finally, after applying all the optimizations that we implemented, we were able to reduce the overall cycles consumed by the parser to about 29.3 cycles, and the number of cycles consumed by the action to about 130.8 on average. And the final throughput that we got was 13.3 gigabits per second. And now, if you compare it with the native OVS, we can see that the throughput is now comparable to the throughput of the native OVS. So finally, after applying all these optimizations, what we found was that now the overall performance overhead was quite negligible, and it was less than about 2%. Okay, so now let us talk about the second cause of from performance degradation in PISCES, which was cache misses. What we did in this case was we actually wrote a program for where the match action table pipeline was just a very simple pipeline where what was happening was when any packet that was coming in for a given port was actually being sent out to the same port. So it's a very simple pipeline. And what we found was like if we sent that packet through the match action tables, then the number of cycles that are consumed by the match action tables in processing that packet was about roughly around 3,000 cycles, which is 50 times more number of cycles compared to the match action cache itself. And also we found that irrespective of the packet size, the throughput was always less than 1 million packets per second. So here you can easily see that there's a huge importance in keeping the flows in the match action cache and making them and force them to be processed by the match action cache and avoiding them to go through the match action tables in the flow path. So again, we further study what were the factors that were affecting the cache misses, and we found two main important factors. The first one was the entropy of the header fields, and second one was the doing stateful operation in the match action cache itself. So I'll talk about the first factor here, which is the entropy of the packet header field. So we loosely define high entropy header fields as those which are likely to have different values from packet to packet flowing through a switch. For example, in the case of end host, all packets originating from that host will likely to have same source and destination layer 2 MAC addresses. However, the layer 4 ports will be varying based on the connection to connection basis. Thus, we can say that layer 4 fields have higher entropy than the layer 2 fields. So again, in the case of PISCES and as well as in native OVS, as well as in the case of OVS, the match action cache is highly sensitive to the entropy of these header fields. A cache rule that is matching on high entropy header fields would result in more misses, thus leading to poor performance. So the objective of this, so the objective now here is that we need to generate cache rules that match on low entropy header fields whenever possible. And the way that OVS did in the native case was what they do is that they already know that the native OVS is actually operating with the three header fields, which is layer 2, layer 3, and layer 4, along with the metadata. So what they did there was they actually knew the entropy of these header fields and the semantics of these header fields. So based on that, they actually converted the match part of the match action tables into stages, where each stage matches on a set of header fields that have lower entropy compared to the header fields in the next stage. So in that case, if you see a miss, for example, in the case of stage 3, what you will do is you will now only install a rule where the match part only matches on the metadata layer 2 and layer 3, and it doesn't match on layer 4. The reason behind it is that because now here you can actually uniquely identify the packet by just these headers rather than looking into the layer 4 headers. So, however, in the case of PISCES, the thing is, because a programmer is writing a program in P4, and for a compiler, by just looking at the P4 program, it doesn't have any notion about the entropy of the header fields that are being specified in that program. It has no information about what is the entropy of these header fields. And thus, it's difficult for a compiler to automatically generate a match rule for the match action cache with the right set of header fields to match on. So again, this gave us an opportunity to come up with another optimization, which was stage assignment. There, what we did was we added annotations and enabled the programmer to specify or tag the headers with their relative entropy. And then the compiler then sorts these headers based on their entropy, and then automatically generates these stages in the match action table. So now in this case, when a packet comes in, it gets a miss, for example, at stage 3, then we only install headers, for example, in this case, header 1, header 3, and header 2 in the match action cache, and we don't install the fields related to header 4. Thus, by this optimization, we were able to actually automatically generate the right set of header fields with the lower entropies whenever to install a rule for a packet that was being matched in the match action table. So, okay, so finally, after all this, we saw that with appropriate compiler optimizations, PISCES was actually able to perform comparable to the native OVS in terms of throughput. Uh, so, in summary, uh, we presented PISCES, the first software switch that allows specifying custom packet processing logic in a higher level DSL called P4. PISCES programs are about 40 times more concise than the equivalent programs in the native code with hardly any performance overhead. So with this, I will conclude my talk and will now go ahead and take some questions. Also, if you want to learn more about PISCES and if you want to try PISCES, you can visit our website at Princeton, which is pices.cs.princeton.edu to download the code and to test it. Thank you.